Adesso sì, puoi verificare. Adesso ancora non credo perché stanno entrando in questo momento.
Ecco, il professor Raugi c'è. Buonasera.
Ciao Marco.
Buongiorno a tutti.
Sì, puoi verificare. Adesso ancora non credo perché stanno entrando. Ecco, ho avviato. Scusate, ho avviato. I just started the YouTube streaming, and when we are all, I'll start the recording. So it's still here.
Professor Pirlo is here.
Yes, ciao Giuseppe.
Ciao Giuseppe.
Ciao, ciao a tutti. Good evening.
Anglan is here. Yes, okay. So how do you manage? You need much more time for presentation, means 15 plus 15?
Marco and I will split the half an hour presentation in two, if you are asking me. Sorry, yes. Mario.
Yes, since I'm looking at the scheduling, and both of you are, yes, from 15 and a half to 16, right? Okay, fine. Then Quartarone and Centi. They are not here, right? No. Quartarone. Not yet.
Okay, if you agree, I'll start the registration. It's okay?
Okay.
Okay. So good afternoon to everybody. I know that there's been a long morning. We finished a little bit late the morning session. I hope it was interesting. And I'm happy that there were many questions and a big discussion. So this afternoon session will be chaired by Michele D'Assisti. Michele is full professor of Systems and Production Technologies in the Polytechnic University of Bari. He has been Rector's Delegate for Sustainable Development Strategies since 2003. And he has an extensive experience in several national and international research cooperation with multidisciplinary groups. He is currently responsible for the first public inter-university laboratory in Puglia for designing and managing territorial and industrial resilience. And I leave him the floor to introduce this afternoon session and all the other colleagues that will speak today. Thank you very much. Michele, the floor is yours.
Thank you, Mario. Thank you so much for the nice presentation. And good evening to everybody. And it's an honor to me to welcome you to this session that I hope will be also, I would say, interesting and stimulating for all of us. It means that we will try to be very precise in our presentation. I hope to stimulate some nice discussion or question. If you don't mind, I will share in this way. It means that we can collect some question at the end of presentation, and hopefully make all the summary discussion at the end of the presentation, if for you is okay. So I can suggest to you to write your question, hopefully in the chat. I will collect all the questions and then we will discuss at the end of the presentation. Okay, for me, it's all for now. And I have the duty to introduce myself in this case, because we are talking about curriculum number 3, technology and territory. And I'm supposed to be the first speaker. Will be with us also Professor Augi and Anglani, Professor Quartarone and Centi, Professor Pirlo, and myself. So I will try to be very precise in my presentation, of course, so to give time to the other for the discussion. So let me share the screen. I hope that you see the full screen. Okay, perfect.
Yes, we do.
So I will start, and with this presentation, which is very, say, specific on in a topic for technologies in sustainable manufacturing. But indeed, you will see how vast and how, say, I would say, challenging it can be. Means that, first of all, let me remind you from when, in Italy at least, because in the world that was very early in this date, it becomes the problem of sustainability. And I always stress also in my lesson, the Club of Rome, which is a very, say, visionary group of scientists that remember us in 1972 of the problem of sustainability. According to today's specification, it seems like a problem of lackness of resources. As I saw in the previous presentation in the morning, mostly sustainability is strongly tied to this issue. It means something which is we are going to consume and not even to replenish at all. Okay, if we stick from this point, I would say draw your attention to a very simple equation, very simple, and I would say also useless unless it's focused on one problem. The first one is that if you're thinking about consumption or resources, the impact on this, it can be defined as CO2 emission, waste, or whatever. It depends on, say, mainly 3 factors. First of all, the number of people on the earth. And I guess you know how much roughly we are. So we must double the number of people every 10 years. So now we are close to 8 billion people. So I guess this is one factor we cannot address with sustainable manufacturing at all. Second is the ZDP, and that is a question or a matter of, I would say, habits of people. And this is not my concern, of course. I'm not the right person able to talk about how to change the behavior of people, how to induce a different, I would say, feeling about our relationship with Earth. But the third part, I think, is very important for us and for me in particular, because it concerns technology. And technology, to my side, can be the only one that may change something in this battle against resource consumption and or resource renew. So the problem is that technology alone cannot solve this big challenge. And we should be really aware of this. So I'm just thinking about, we are thinking about, I will show how a group in Italy is working on this subject, but we must be really aware that the strongest impact on sustainability issues may be derived from the other two aspects that I referred before. So we are just talking about small effects coming from technology. Let me show how we can think about sustainability issues also from manufacturing point of view by simply thinking about this structure, this systemic view of our society. And mainly, I usually refer to a dynamic view of the problem, which is in the rate of extraction and the rate of replenishment. This is a very important aspect of the question. We may think that equilibrium, because we are talking about equilibrium, depends on the rate of something, in a change of something, not essentially in the mere quantity that change as an overall figure. So if we see the system this way, we can think about manufacturing as a subset of these big issues, big picture that I gave you. What are the main factors of a transformation process and how we can interpret a transformation process, which is in manufacturing? First of all, we have material input, material in output. So, and material may be, as we already know, renewable or non renewable, primary or auxiliary. But in any case, it belongs to Earth and comes back to Earth in a different state. As a finished product that we may use as waste or scraps. Then we have energy. Energy is always necessary for any kind of activity in our life. Energy is again resources from Earth in a different form, different shape, but it is always resources. And here again, we have coming from Earth, going to Earth. And this is very important. But in this transformation process, there is another element which sometimes is not perceived as say, physical one, which is information. But indeed, we sustain as technologists, but I sustain, which is one of the most important in the issues of sustainability. Because information is the way in which you do things. It means that you can do in the right way or in the worst way or in the bad way. So information is the true and very important issue of sustainability. And here again, we have information in and information out. Out is information is typically experience. So maybe that also for manufacturing operation, we can think about outcome or scraps from a transformation process, the information, sorry. And what are the factors so that we can summarize in this process of transforming and manufacturing material? Is matter, energy, information, but also human resources. This is another point that I would like to stress, since we are typically referred to as technologies or say people related to machines. But now, even us as technology, we are talking about human resources as a part or the main part of the transformation process. And you know, why this is very important, this point, because human resources are the leading factor in the transformation. And if we think about human resources, let's say, for instance, the smart manufacturing. Smart manufacturing is a typical example where still there is the task of transforming the factory in an unmanned factory without man. But smart manufacturing at the present is simply trying to cooperate with man. Means intelligence, artificial intelligence is cooperating to support man. So human resources are in fact a production factor in manufacturing activities. And this has to be perceived very clearly in order to reach a real manufacturing activity and sustainable manufacturing activity. Of course, now we can define, according to SDG, the 12th SDG, as a sustainable manufacturing as an economically sustainable process that minimizes environmental impacts, conserving energy and natural resources, and improving safety for the community. But, you know, this definition is really, I would say, large, is very wide. So it's very difficult to solve in concrete, in effect, this issue of sustainability in manufacturing. So how can we address this issue? First of all, we have to think that as a manufacturing as I told you, a dynamic process, but also a process which depends on the path that you follow when you go from initial state to the final state. That means that there can be different paths that you can follow for reaching the same state, which is the final state is the state in which you reach the function you are looking for a product or a process. So this is the true challenge in research by now. It means that we can obtain the same object with different technologies, with different processes, even with different materials. The question is how and what is the best path to follow in order to satisfy the transformation we are looking for. And as you see, there is the function, the F, this is signed here, which is not already defined at all in several fields of our life, in several activities, from transportation to medicine, to agriculture, to aerospace, also even for tourism. In each one of these sectors, we need manufacturing. We need a transformation for doing things, because we men use things for doing our jobs or activities. So maybe the third factor was referring to in the Iot equation can be reached if we are able to define the best path to follow. And that's the issue in research for you that are young students and young researcher, to solve the future question of sustainability. Let me also point out that the degree of interest about sustainability may change according to the life cycle phase of our production cycle, as you can see here. So you can have producer attention, which is different from consumer attention, which is different from society attention. And depending on the stage, you may have different assets on which to strive and to consider. So it's very important, these slides, to remember us that it's very important, the systemic view in all the problems that we face. Also in the manufacturing, because I typically am focused on the production, means one of the fourth part of this slide, but it is not enough. I need to consider what there is behind, what is before, okay? So it's very important issue to point out. And finally, I saw that you already learned that there is NR model, means 7 hours, 3 hours, 6 hours, 7 hours, 8 hours. The R factor seems to be very important, but what is really important is the relationship between the R's, I mean, how they cooperate to the same issue. And here there is some example of this framework with the world, and mainly, I step with the future. Next slide, the relationship between R, recycling, which is strongly related also to direct reuse and remanufacturing. Let me say that this picture is not complete at all. There is also room for thinking about new solution and new advanced manufacturing solution for striving and improving this approach. So we will refer now in the example that I will show you, and I select our group of technologies in Italy, because I think it's much more interesting and I would say useful for you to see a group of people which are all together working in synchrony for sustainability. So that's why I decided not to give a standard lesson, but to give also example on the ground, from the field, from our group of research and study. So I just give you the flavor of some of example very, very swiftly, because I have not much time and because I wish to give the room for the other discussion. So it's better to be fast, but there will be enough to let you see a sort of picture of what is going on, at least in Italy, which is mostly similar to what is going on all over the world. Polytechnic of Milan, they are thinking about controlling machines. So if you see here, over a working power of 12 kilowatt hours, the idle power, means when a machine is not working, is something like 1/3 or closer to 1/2 of the overall power consumed. So it's very interesting to think about. It's like when you switch on and switch off your car at light, when you stop at light. It's similar to the problem. But if you multiply to the number of operations in manufacturing that you do, you may think about how many tons of power you will save if you think how to solve this problem. And this is a very interesting point of view. So simply by noting this, if you see, this is a matter of information. He stands for information, because you need to monitor, to learn, to model, and of course to measure. So it's something like that that belongs to the use of information in manufacturing, as I referred to you before. Then another sample, very easy, is a particular technology, very simple, is sort of stratification of metals to form a part, which is a blade in this case, in our foil. And in this case, they find out the best solution comparing energy consumption during production between this new technology with a standard technology. So we may think that some technologies we are using now belongs to the very far past, maybe centuries ago. And maybe for simplification, maybe for not strong research on new field, there is no room now to easily change the way you produce products. If you think new technologies, T is for technologies, then you may change the way this approach, and maybe you give a small contribution to the sustainability issue that I referred before. Another approach, I do love so much this one, because a colleague of mine from University of Bologna introduced the idea of slow manufacturing. You know how time is a production factor. In our minds, time is always a must. Reducing time is a must for production. But sometimes you may think in reverse. You may think of quality, of the value of slowness. And that's exactly what this colleague introduced. So U is here for as human, as idea. So I do love this application because it tried to endeavor and to give value to the the slowness in production, according also to a sort of say analysis that he did in a district of Leda, in this case. Again, from Politecnico Milano, the idea of teaching factories, which is always applied for real operation, but the teaching factory is technology plus human, because human capital is very important in sustainability battle. If you feel how to solve differently the problem, the path I was referring to, that you may change your mind in the way you are producing. And I just go fastly, let you an application of mine, just to try to give value to PV panels. You know how many production of energy resources are all over the world. This is a pattern that works and simply sustainable because use hydrogen and nitrogen, frozen nitrogen. So it's very sustainable and effective. Other applications look at reducing consumption of material and reducing the accessory or support materials like lubricants or like the energy by optimizing production. And just please take it as pictures. Don't try to understand even the figure or the value of the picture I show, because there is no time and I don't want to go deep inside what I show, but let my words explain you this slide I'm showing. So here we are minimizing the production factor, the material that you use to cool during production. Again, another way to think about how to reuse product by reshaping. So it is SPF is a technology which makes incremental forming, means change slowly the form, the shape of a product to reuse in a different life. And so we may use these new technologies like this one, or it is better shown here. We may change the way which we produce things or transform things to reuse for a longer life. And finally, we can think about also to this sector of the footwear, when the advanced manufacturing technologies may change the way and in which we reduce consumption of materials and improve also the function of the use of products. So I stop here for myself. I just will look at question from the chat if you want. And I give the room to Professor Raugi and Professor Anglani to start the presentation, I guess, in time. So I earn 4 minutes, so you have much more time to present yourself and to present your presentation, okay? Thank you.
Okay, thank you, Professor D'Assisti. I am Marco Raugi, Professor of Electrical Engineering at the University of Pisa. And together with other colleagues, I will now try to share the screen.
It's okay.
So now should be right.
Works.
Okay. So this presentation was made with the contribution of the 4 professors listed on the screen: myself, Professor Norma Anglani, Professor Michele Bonin, and Professor Antonio Testa, while myself and Norma Anglani will make the presentation. The presentation will begin with a brief introduction on the topic, and then proceed with the 4 important examples just to give some suggestion and some ideas of the important problems that are related to electricity and decarbonization. So just few words, because audience is a very wide and different educated formation. So just few words to try to give everyone the possibility to understand the framework in which we are moving inside this strange world of electricity. So it is very wide known, every one of us know how many electric devices are in our common life every day. So sometimes, especially those who are not science educated, are trying to confuse electricity with energy. But actually, this is not the same at all. Electricity is a form of energy, and is a form of energy that is not available in nature. Primary energy forms are the fossil ones, oil, carbon, gas, or renewable ones. Most of them known are wind and sun. But electric energy is extremely important because it's the way by which the energy are transferred from the places where the energy is available, and which is the central, the plant where the energy is produced and transformed from primary energy to electric energy, and the place where the energy is used, is consumed, that are cities or every other kind of buildings that use electric energy for their own habits. So energy is a carrier of, and electricity is a carrier of energy, and is not energy itself. So this is the first important point that everyone must have clear. But however, since it's the way in which energy is transferred, it is at the heart of the problem of energy consumption, production, transmission, and use. So historically, at the beginning of the past century, electric energy was produced in a limited number of places and then directly transferred to end users. But has the awareness of the fact that the fossil energy is more and more consumed, and there was a necessity to use renewable energy, so energy that not consumed our planet, then other possibility to produce electric energy was introduced into the system. And this, of course, complicates the control of the system itself and the monitoring of the electric system itself, because it was built at the beginning for in a given scenario, and now it's more and more, the scenario more and more changes, and the system is more complex, far more complex than in the beginning. Moreover, while the generation of electric energy is made by a very high density of energy from fossil combustion, the renewable energy has a typical characteristic of have a very low density. And then what does it mean? It means that a small generator of electric energy from renewable sources are distributed into the place, into the space, into the territory. And this more and more complicated the system itself, because you see in the screen at right, the difference is, this is a graph that try to explain how the system is made. In the beginning, it was made in that way, and now it's completely changed. From the sustainability point of view, electrical technology is related to some SDGs, and of course the SDG 7 that is centrally based on energy, but also with the work, because the availability of energy influences the work and the kind of work and the growth, economic growth. And also it's very important for our cities to give it the possibility to make all the people to have all the possibility to have a high quality life and improve their welfare. And also, of course, the consumption and production. The production system also is clearly based, as Professor D'Assisti clearly said before, is fundamentally based on the availability of energy. So now I will begin a description of some important fields of research inside this world of electricity that is very wide. The framework of the energy community is quite recent in this sense, and because it is a kind of aggregation of people that is more and more grown in recent years. By definition, a renewable energy community is a form of non-commercial association. It's a legal entity of families, also of small, medium enterprises, which share one or more plants for the production of renewable energy and can produce, consume, store, and also sell these electricities. What are the values of this energy community? It is very important because this energy community combines several aspects, not only the technical ones, this is very important, but also the social ones. Indeed, the commitment, the role of sharing, and the informed participation is at the base of this topic. Fundamental indeed is to share energy. Share energy is a way to reduce energy consumption from a certain point of view, optimize the energy consumption in the sense that energy is more and more less wasted, and also try to push all of us to change our habits for the common good. And this is very important socially. Try to make all of us think not only in terms of ourselves, but only in terms of a community, a part of a community. So it's very important in this sense to make information to all of the people, and participation is a key concept. And let me say, for people who are aware of science, that this is a reformulation, it's nearly a joke, for the third principle of thermodynamics, which states that energy is not created, not destroyed, okay, but in this sense, it is shared. So these are the three dimensions of sustainability stated in the Agenda 2030, as all of us probably know. The three parts: economic, social, and environmental. And the energy community has something to say in all of these dimensions. Environmental, of course, because renewable production is encouraged, zero CO2 emission. Ideally, of course, this is the goal. More energy efficient and progressive electrification of loads. Social, as I already stressed, the distribution to the REC members of the part of the benefits that the energy community is able to guarantee. And economic, of course, because there are benefits that reward the share self-consumption and return on the investment and continuous improvement. So let me now introduce the pillar of the energy community. That is, I would say, all of us, a prosumer. What is a prosumer? A prosumer is a consumer that is no more only a consumer, but is only a producer of energy. And if each of us will become a prosumer, things could be much better in terms of energy savings, because we would try to see that how it is important to improve energy efficiency in the buildings, cost savings, because more efficient behavior, we could buy green. Buy green means buy energy produced by renewable energy, and automation. And also try to learn how to produce energy. And if we produce energy, we'll be more and more aware of the value of having this energy and not waste it. So in this sense, the prosumer will be the enabling subject for the green transition. And that because the role of a prosumer is that this person, I repeat, all of us could be a prosumer, will have great environmental involvement, more and more aware of the importance of be green and behave green, and was more and more responsible of this energy consumption. So this is a sketch of what is the situation in Europe, at least now, because energy community is something that already exists. And you see that there are many, many examples of energy community in Europe, more in Germany than in other states in Europe. But an important view is the right part of the screen, where you see that this bar are the quantity of renewable energy owned by utilities. You see that most of energy is owned by important utilities in the most important state in Europe, but you will see the green bar, that is the citizen energy. What is the citizen energy? The energy produced by persons that are mostly engaged in energy communities. So if this kind of entity will more and more be adopted by, because it's voluntary, of course, is adopted by people, then the property of renewable energy will be not more only by big companies, but also by people, and will be distributed. And so this will open a very big issue for the distribution of responsible and properties and riches, because energy is richness, of course, and open many questions in the distribution, not only of energy, but also on the possibility to influence the sustainable development. So also it's very important to say that due to this kind of framework, energy communities is an area where multidisciplinary is necessary, because there are not only technological problems you see in the first topic. These are typical engineering problems, because regarding the combination and sizing of renewable technologies and plant, and also storage, but also aspects regarding law and social science, because I already said that people should try to vary their energy consumption for the benefits of the community. And also it is important to try to see which kind of incentives could be useful to enlarge the possibility to create this community and to create prosumers. Of course, economics is also at the base, because at the end of the day, it is important at least not to lose money. And also it's very important due to the complexity of the systems to have information for the control and management and monitoring of the network. So now let's start with another topic, that is e-mobility and smart grids. And smart grid is what I already sketched before, is the electric grid is the way by which electricity is taken from the center where the energy is produced and brought to the users. It's smart because it's more and more difficult to control and monitor it. These are a sketch of the complexity of the system and the importance of data and on how these data are elaborated. So it's very important, the data science in this sense. And also it's very important, it's one of the topics that probably in the last years became the more and more important also in the media, the air mobility, the electric mobility, which is used to reduce the production of amount of CO2 emitted. And electrification of mobility could be very useful in this sense, because as you see in the screen, the vehicle efficiency is more and more becoming important. The e-mobility, of course, deals not only with cars, but also with ships and airplanes, because more and more, just not to pollute the atmosphere, it is very important that also airplanes not produce these emissions. And so there are studies that try to design airplanes and ships that are supplied by electricity. Also, this means that there should be a wide diffusion of infrastructure for the charging of this kind of distributed systems. So smart grids and e-mobility are strictly related one with each other and are fundamental pillars of the transition towards a low carbon society, because e-mobility is to become an important new form of end use of electricity. Smart grids, of course, will become the main energy source for transport. A large-scale adoption of e-mobility is crucial for the infrastructure investment of smart grids and also to be profitable. And not only there is the connection from the grid to the vehicles, but also the reverse, because electric vehicles could be important components of distributed grids, provide the so-called ancillary services, because also vehicle can transfer energy to the grid and not only the grid to the vehicles. There is also a problem, of course, in second life use in the storage system. The batteries mainly today is this kind of storage system that are used, or even if hydrogen is one possible way to store and use the energy. But there is, if the energy system more and more became popular, of course, there should be a big problem in the emission of these batteries. And so this is a description of the topics, the main important topics that are around the decarbonization, the e-mobility, the smart grids, and in the middle, the electrification, digitalization, efficiency, renewable energy, hydrogen, distributed generation, and so on. There are a lot of arguments that are subject of research to optimize the performance that could enable the e-mobility and the efficiency of the smart grids in this sense. So now my first part of the presentation is finished, and I will leave the stage to Norma Anglani. So please, Norma, continue.
Okay, thanks everybody. I will share my screen if you don't mind. Let's see if
I will stop my presentation.
Okay, let's see if I can make it. Okay, share. Let's see. I don't know, where is it? Okay, let's see if I can move everything around. So, can you see my screen?
Yes, yes, okay.
Okay, it's perfect.
Okay, so.
Please just take a look to the time. Huh?
So, thanks, Mark. Yes, yes, I will just start my time right now, and I will try to be as fast as possible. Anyway, thanks, Marco. My name is Norma Anglani. I'm from the University of Pavia, and as well as my other colleagues, I want to welcome you too. I will go on with the second part of this presentation, focusing on a couple of additional key issues relevant from the electric research standpoint. So far, you have been exposed to the topic of e-mobility, smart grids, as well as energy community. Now, I will introduce you to other key issues again, in the electricity sector, the so-called microgrid. So here you can find a simple representation of what a microgrid is. Micro stands again for small, and the size is given in terms of power. So how much power we deal with. It goes from a few hundred megawatt down to a few kilowatts. And the grid is the infrastructure energizing the different end user. The infrastructure is made up of a supply side who is providing power, so energy, which is power over time. And at the end, on the other hand, there is who is using this electricity. So with respect to who is powering this network, we can have what is called a grid-connected microgrid. So there is a connection with the main grid, with the centralized power plant, as Marco was showing you before. But there is also the chance of using this DER, which stands for distributed energy resources like hydropower, solar panels, wind panels, but also fuel-based generators like the diesel generators, and all different kind of storage like batteries, fuel cells, and also sometimes also the electric vehicles in the so-called V2G, vehicle to grid configuration, where the vehicles can be either a loader, so someone who needs energy and power, but also can provide ancillary services like providing energy back to the grid. As I said, the grid can be seen in this way, grid connected, but also can be considered as islanded. Islanded means that there is no a main grid upstream. You can be energized by local kind of resources. this is a very powerful way of reaching almost everywhere in this way. So you don't need a main centralized power plant, but you can energize locally, potentially, all different users. And there is an increasing demand for highly reliable and sustainable power supplies under the fast development of smart and connected communities in recent years. Mainly, the global trend of urbanization has been posing significant challenges on the heavy loaded and very often aging power infrastructure in our cities. You have been you saw today in the morning, talking about urban areas and make these areas more sustainable. But we know that UNO, United Nations, forecast for the next 15 years an increase of almost 1 billion people. So these will pose a very strong challenge on the power and energy system, provided that the infrastructure are almost operating right now at its physical limits. But this is not only an issue related with developed country. This is an issue that involves also developing country, because if you think about rural areas or isolated areas, the main issue is how to be reached this area. And you have to bring electrification in a reliable way, and the supply of electricity is likely to be affordable and sustainable. So this kind of infrastructure can be the one able not only to, let's say, overcome problems like outages, blackouts, that can be the consequence of a weak grid, because there might be some threats that can come either from the weather, extreme weather events, or cyber attacks, or faults of any kind, or disasters. So the microgrid is something that can provide and can be a promising paradigm of electricity resilience. Resilience, this word that you have been hearing a lot today, and is able to keep a local community service up and running even when something disruptive happens on the main grid, in case you have a grid connected microgrid. But when there is no main grid, as in this kind, then the microgrid happens to be the only way a local community can be energized. So what are the main features of a microgrid? Well, actually, there are many definitions. I want to rely on the SIGRE 2015 one, which is a definition according to which microgrids are electricity distribution system containing loads, distributed energy resources, as we saw, such as diesel generators, but also renewable energies, kind of plant, storage systems, and also controllable loads. That all these systems can be operated in a controlled, coordinated way, either while it's connected to the main grid or when it is operated islanded. So there are very many distinct advantages to customers and utility when a microgrid is set up. Of course, it improves efficiency and minimize the overall energy consumption. Why this happens? Because you don't have to rely on long lines, on long network, and so you don't have to rely on centralized electricity production, but you produce your electricity locally. So this is a way to improve efficiency and also to improve consumption, and to reduce the impact of the electricity production, because you can make the most out of all the renewable sources. It can help then, here I will be talking technically, but to relieve congestions when electricity needs to be distributed and it has to be done in the best way. So it involves a lot of problems related to also how to make a safe supply of energy. But of course, it is a very cost-efficient way of infrastructure replacement. So there are technical challenges, as I was anticipating, like being able to provide a good quality for the electricity you are providing, which should be efficient, of high quality, but also should have less cost than coming from the centralized power plant. And renewable energies are much better controlled in this kind of infrastructure than if they were from a centralized grid. There are other issues related to how better control the variability of renewable energy and also the variability of loads. So how to control the match between demand and supply. And there are really many objectives objectives and targets that should be optimized in the long run. One of these challenges is what you have been already exposed, is the resilience, that here is called the resilience challenge, which somehow can be also a link amongst different disciplines. For instance, in harsh environment, you need to account for different targets, and so you might need different methodologies in order to make an early assessment of how sustainable a microgrid can be. Yes, microgrids offers a lot of wide range of challenges, among which even the definition of a resilience, there might be many ways in which we can account for the resilience of a microgrid. So methodologies to make a good evaluation of these technologies have to take into account a lot of relationships among different parameters, and sometimes they are not so easily quantifiable, and also economics. So, there is a lot of different challenges that can be won together. Another kind of research field related with electrical technologies is the one dealing with the so-called IoT, Internet of Things. I can guess that you heard about that or you talk about that. IoT is the interconnection via the internet of computing devices embedded in everyday objects, enabling them to send and receive data. But these can pose different problems. These are likely wireless devices, so there is no really an external source available. So you need to make it really small and remote, all the different appliances, helping these devices to be energized. So small batteries usually are used but they are difficult to be replaced sometimes, and they are also a very hazardous disposal to deal with. So one solution is that this sort of things can be self-powered, and or the batteries that are needed can be recharged by scavenging energy from the environment around. So trying to pick up the energy that is around, sorry, just here. And this process, particular process of scavenging energy from the surrounding environment, is so-called the energy harvesting. Energy harvesting is a way to provide energy, let's say, for the recharging of batteries, and can rely both on very mature technologies like wind and solar. These are mainly outdoor technologies, and they are related with large installations. But there are also the radio frequency and here the thermal gradient, which are way that are widespread, but they are low power density. If we think about, for instance, the human motion, we can catch the human motion and try to make get out energy out of that. It's really widespread, but it deals with the very low frequencies, and devices are very hard to make them smaller, so miniaturized. And then there are also which are really widespread and which can provide a relatively high power density and also can be miniaturized, are the mechanical vibration and acoustic vibrations that can be turned into energy. Why energy harvesting is becoming a solution for the future? Well, in 2017, 1.5 billion already of the market was dealt with the energy harvesting. And this is important because if we look at this graph, which can look like a little bit tough, but it says that the batteries comparing with ICT and telecommunication technologies is showing a less fast pace of development. Well, if we think about the challenge that batteries pose, then energy harvesting can be a solution. And it is a very highly interdisciplinary area of research. So Internet of Things is a paradigm for the future in terms of the potential that can provide us with information. But the problem with batteries, well, the chemistry in our colleagues in chemistry will provide us new solution, of course, but devices like the one that we can work on with respect to energy harvesting can be a very powerful solution for these devices. So I just want to sum up by saying, first, today I read someone writing in the chat that one of the problem is lack of technology, but also behavior, as Professor Motta stressed this morning, and also Marco before. Well, the research challenges of this curriculum aims at providing solution to this lack of technologies, trying to investigate different aspects of them on the energy, production, distribution, and the use side. Electricity is a key factor for decarbonizing Europe, but not only Europe. And many challenges can be overcome but are also posed to our society. So the transition to electric mobility is an essential step toward the decarbonization and will have a significant role for the future, as well as smart grid, IoT, microgrids. I just want to end up by saying that be engaged, as today Professor Grossi was saying, because these days will offer you a great opportunity to be inspired and involve also the other into your PhD project. So I hope, I know that I've been a little bit late, but I can take maybe question later. Thank you very much.
Thank you. I suggest either Marco and Norma to have a look to the chat from 3:40 up to 4 p.m. So you can prepare eventually for the discussion at the end. Now introduce Professor Quartarone, Professor Centi. Okay. If you kindly switch on the camera. Eliana, are you here? Okay, okay.
Okay.
Ready?
Can you hear me now?
Yes, perfectly. Everything is okay. Also the video is okay.
Okay. First of all, good afternoon, everybody. What I would like to deal with you today is how chemistry and energy are correlated between them, and in particular, how chemistry can boost a sustainable development and the transition to clean energy. What is energy? Energy is the ability to do work or to heat something. As you know, there is a lot of energy source. Probably chemical energy is largely used because it's based on the simple conversion of what is available in nature into more useful form. For instance, the fossil fuel, the natural gas, the batteries and wood biomass, and so on. All these chemical energy are used to produce work or heating source or electricity source for the most used application today, which are stationary, portable, and mobility, which means transportation, industrial sectors, electrification and heating of residential and commercial building, and electric power that are assisted by this chemical energy, in particular by using this type of materials, which are the fossil fuel, which unfortunately have, as all you know, important critical and issue. As for instance, one is more technical, that is the efficiency of conversion. Chemical heat or chemical energy is not so efficient as we can expect. And then there is a depletion issue, because this kind of energetic sources are not infinite and not always available. Probably standing to the Haber prediction, the peak of ability has been already achieved. And last but unfortunately not least are the climate issue, because fossil fuels are so negative in impact in terms of environment to the CO2 emission. So what chemists can do is leave out this kind of materials, for instance, the fossil fuels, to move towards a greener approach, which fit with what the European policy is doing during the last 2 years by building up a new policy context that has been signed by all members as the European Green Deal, which aims at improving the well-being of people by becoming a climate neutral society by 2050, and in particular by developing clean products and clean technology stimulated by green chemistry, chemical approach. This will be carried out by step through a transition to clean energy and a route to fully decarbonization, which is envisaged by 2050, coupled with economic growth decoupled from resource use. This is a very, very important point. So the Green Deal, as we know, is an integral part of the strategic agenda of the United Nations in terms of sustainable development goal. In particular, the relevant goal is the number 7, respect to which the research innovation will be funded in order to support e-mobility, smart transport, batteries, energy storage, clean energy, in addition to the renewables, in order to ensure access to affordable, reliable, sustainable, and modern energy for all. What is a variable renewable energy source? Is energy which comes from a continuous flows of energy occurring in a natural environment. For instance, sun, for instance, tide, ocean, wind, biomass. And there's the fundamental characteristics that, contrary to the fossil fuel, is considered inexhaustible. As we can see from this graph, when there is a comparison between the fossil fuel and the renewables that tend to be always available. Among the huge family of renewable, of course, the solar energy is the most abundant because the surface of Earth may be struck by 1,102,000 terawatt, and is, of course, an inexhaustible source. It has been calculated that is guarantees for more than 4 billion years, and is naturally well distributed over the planet. The technology which is based on the solar energy is the photovoltaics, which converts the energy from sun into electricity. This is actually made by silicon as the mainstream technology. All the solar panels we see around us are made of silicon, because actually is concretely the highest conversion efficiency. However, in order to decrease device costs and to be more dependent than silicon, which is a critical raw material mainly located in China, emerging and alternative materials are deeply studied by chemists during the last years. For instance, organic materials or emerging systems from the thin film technology. However, despite the renewables are so enormously available, they are also intermittent. And this fluctuation must be compensated somehow, because there is a mismatch between the energy source and the energy needs. This can be made, as already you have seen in the very nice talk before, by an integration between the renewable energy source and the energy storage technology into a grid, in order to compensate some fluctuation and to provide a fully available energy also in case of seasonal dependency or day-by-night dependency and so on. This at level of smart grid, but also in case of gigafactories, so industrial sector. And the idea of the integration of renewable and energy storage for a chemistry must be strictly related to the sustainable perspective, which means to think in terms of closed loop recycling pathways in the device life cycles, and eco design of a sustainable device, meaning the use of 3R, recycling, remanufacturing, and reuse, in order to reduce the waste material and the disposal to be treated. Which kind of energy storage technologies are available now? There is, again, a huge family of possibilities, but the most important seems to be the electrochemical and chemical storage technology, which means batteries, in particular lithium-ion or post-lithium ions, and also hydrogen, because they are the key technology which concretely may enable a climate neutrality by 2050, meeting with, the targets of Green Deal in terms of acceleration of the shift towards sustainable and smart mobility, to help supply clean, affordable, and secure energy by reducing the CO2 emissions. So we are talking about zero emission technology, and also by favoring a circular economy in terms of materials. So, but what is a battery? A battery is a simple, very simple chemical reactor, electrochemical reactor, where some components which you find in the negative and positive electrodes may react all together through an electrolyte separator here. And from the energy, chemical energy arising from such process, we can produce electricity. Electricity that can provide us for power something, for power in some application that can be heat something or give propulsion, for instance, for an electric vehicles. And you can find batteries, lithium-ion batteries everywhere. In particular, they were born for powering the consumer electronics, but now they are widely diffused due to the electric mobility, which is growing ever and ever during the last time. And for this reason, there is a very great global battery demand, which is expected to grow in order to fit the energy requirements coming from this new technology devoted to reduce the greenhouse gas effect and the reduction, and emission. So you find lithium-ion batteries in portable electronic device, which can be, for instance, which require more and more energy to be stored, and also high energy density, because your devices are even more complex, for instance, from the phone to the smartphone, more complicated computers. So all this technology behind this device require more energy delivered by the batteries. But you can also find in particular, and also in device, medical device, for instance, or also military device, where the batteries technology is very required. But in particular, you can find, of course, larger and with higher density in the e-mobility, which thanks to Tesla has been boosted very faster during these last years by reducing the production cost of the electric car, which may be, which is decided in two types of engineering, an hybrid plug-in hybrid systems, where a battery is combined with a conventional engine vehicle in order to use, for instance, the battery, the electric propulsion during the rush hour in the traffic of the city, so to reduce pollution. Or, for instance, and a fuel tank, a fuel engine motor during the largest distance, or eventually also the electric vehicles with batteries, traction batteries, which may be easily recharged, for instance, from the electric grid overnight. So reducing the load on the electric grid. But batteries are also used on a nanogrid, for instance, in terms of residential application, where a series of batteries may be integrated with, for instance, hydrogen, which are charged from the electric grids to compensate the fluctuation of your solar panel put on your roof of your house during, for instance, winter or during night, and may be also used to maybe, of course, recharge back from the same solar panel. The chemist in this kind of technology may work on the improvement of the materials in terms of chemistry neutral approach by designing greener materials, may be easily manufactured with the support of artificial intelligence, and also may easily recycled, as we already seen before, taking into account that the battery is fully made of critical raw materials which are strictly related in some geographical site, for instance, cobalt in Africa, or lithium in South America, or silicon in China. And this is a very important point for Europe in order to be independent from the third part, so for the third country. So the recycling aspect is very critical in order to recover the end-of-life materials. Finally, another important chemical technology which can make energy cleaner is the hydrogen, towards which Europe is putting an investment priority and has a priority role with respect to other countries, for instance, Japan or Asia more in general. Again, hydrogen is an energy carrier, which is related to, again, a chemical conversion, a conversion from chemical energy into electricity, or also the reverse process from chemical energy, electric energy into chemicals. If we use a device that we call the fuel cells, a sort of battery that is based on this very but wonderful, simple reaction that is the combination of hydrogen and oxygen to form water, we can produce electrons, which means electricity, which again, like in case of battery, may be used for electrify something or power something and so on. But if I use the reverse process, I can produce, by means fuel cells now become an electrolyzer, I can produce green hydrogen. That is a very important energy carrier that may be used to as a renewable source in order to exploit and deploy at a large scale across all hard to decarbonize sectors, like for instance, the heavy industries. So hydrogen may be used in a fuel cells, as already Norma explained before, but also in case of electric propulsion. So you can have electric cars that work with hydrogen, with the fuel cells, by replacing your fuel with hydrogen, with a better and a greener carrier fuel. There are a lot of vehicles that have been designed by Honda and Toyota in Japan, Hyundai in South Korea, and also many industries in Europe. Unfortunately, with respect to conventional electric car based on batteries, there is a problem of infrastructure, because hydrogen-based vehicles need to hydrogen refueling stations, which are very complex structure made of several rooms that we can briefly present in the few last slides. An electric vehicle works with a fuel cell, where inside which hydrogen contained in a particularly and optimized the well-sealed tank react with oxygen coming from the air in a very simple reaction, as already said, producing only water as byproduct of the reaction. Water is vapor. So is the perfect zero emission concept. Best in terms of zero emission with respect to battery, a conventional battery electric car. How a hydrogen refueling station is made. This is probably a very interesting idea of grid that we can is a reality, in particular in some country of North Europe, I think Denmark or Germany. This is the hydrogen refueling station, where the hydrogen is before stored in large tank as gas. Then it should be compressed, so the gas moves through this pipeline in another room where the gas is compressed by means of several chemical process or also mechanical process. Then the liquid hydrogen is transferred to the vehicle refueler at high pressure in order to refill the vehicle, which needs hydrogen for its propulsion. It's, of course, true that this infrastructure that you can see here in the reality in Germany is a quite not so cheapest infrastructure. But if we think it's inside a grid, this start to be convenient, because the hydrogen refueling station may be integrated in on-site hydrogen production plants, which integrate, for instance, the renewable sources, wind and sun, in order to power an electrolyzer which may split water coming from some reservoir in hydrogen and oxygen. Hydrogen that is moved toward the hydrogen refilling station in order to fill your vehicle. And from the vehicle, you can obtain water again as product for your reaction that may be again put in this closed loop in the electrolyte. So this is a very interesting and greener technology based on this kind of new energetic approach. So just to conclude, hydrogen versus battery, who win from an energetic and also chemical point of view? We can say that they are not competitive technology, rather they are complementary, because there are advantages, some open challenges still to overcome in both of them. In particular, probably hydrogen is more concretely zero emission technology with respect to the battery, which however is cheaper, is more economic with hydrogen. But for instance, hydrogen fuel cells may be faster fueled with respect to a battery that require overnight to recharge your battery. So there is also a range anxiety different from one technology to another one. And just to conclude, hydrogen probably is the best choice in terms of large transport, so to propulsion in large trucks or buses or trains, for instance, which is a reality in Italy within 2 or 3 years. And of course, in large scale, in terms of power stationary application or stationary plants, battery instead are preferred in light transport, so passengers car or taxi fleet, and also in small medium scale stationary application. So to conclude, how chemistry can boost the transition to clean energy, to moving from, of course, fossil and polluting materials which make chemistry so ugly, towards a green chemistry approach, but in a multidisciplinary, interdisciplinary approach in integration with other disciplines, for instance, engineering, in order to facilitate what now is the state of the art in terms of energy system, which means a linear and wasteful flow of energy in one direction only, from the producer to the consumer, towards a future integrated energy systems, which is not linear but circular, where energy flows between user and producer, reducing wasted resource and money, with 3 main and important characteristics, which be the game changer: a more efficient and circular system where waste energy is captured and reused, a cleaner power system with more direct electrification of end-use sectors such as industry, heating of building and transport, starting from below, going from the start, from the materials that the chemistry design, which should be greener and more environmental friendly. And of course, finally, a cleaner fuel system in order to make possible this transition also in the hard sectors like heavy industries and transport. So I'm sorry if I've been late, but I can stop here, and I thank all of you for your kind attention.
Thank you, Eliana.
Okay.
There is also Professor Centi.
I'm here.
So unfortunately, we are a little bit late. So if you can manage it some way, it would be nice. Thanks.
Yes, I will try. I hope that you see my screen. You see my screen?
Yes.
Okay, perfect. Okay, so let's try to be a bit short. And the first question that I think that will be important is why was put together these topics, chemistry and catalysis. Because of course you will see that there are shared many common aspects. Catalysis is an important part of chemistry. Of course, also is important part of other topics from engineering, physics, and other, but let me say the roots are in chemistry. Few words about catalysis, just because some of you probably are not fully aware of catalysis, what is exactly. So the concept of catalysis is that is an element, normally a solid, on which you absorb some reactant, catalyze, so accelerate the transformation of these, and in a cyclic process, in a cyclic event, because at the end of the catalytic cycle, you reform exactly the catalyst, starting catalyst. But of course, in this transformation, you are introducing a new path of transformation that you see on the right, in which normally this is a path which has a lower activation energy. So this already explain what is the role of catalyst, is to provide an alternative path of reaction, which is typically is energetically more favorable, but also in this way you can try to select and to go more efficiently to the target that you have rather than to alternative paths. So the keywords are acceleration. So you increase the rate of reaction, you control the path, so you increase the selectivity, and you save energy because you need less energy without the catalyst. You reduce the waste because you have a better control of the reaction, and you of course you save also resources in general. So these are the elements why is integral part of any sustainable objective. So you see here, for example, an example of industrial catalyst. You see that they have different kind of shape, which are illustrated here. But the main concept is that to achieve a catalytic process, what you need is to control a very complex process, which is multi-scale. You need to control the nature of the element of the catalyst itself, but then you need to control the other characteristic like porosity of the material. You need to put this in a catalytic reactor, so you need to control all the process of transfer. So in this way, you have a process which is quite complex, and you need to have an optimization of all these factors. And for this reason is a multidisciplinary topic. So and the other element which is important is that for this reason, you have also multi-scale. So here you see in terms of time scale, you have a very large variety of approaches with a different time scale that you need to control, and also in terms of lengths, which are quite different. For this reason, you need to put together many different competencies, going from electronic to design, to nanoscience, to engineering of the material, to engineering of the process. Why is fundamental for sustainability and climate change? I think that there are many demonstrations, but this I think that is one which is quite clear. One of the first main large-scale process, catalytic process, is the synthesis of ammonia, something like more than 120 years ago. What is important, you can see here, what is the kind of prediction that you have in terms of food that you can produce without fertilizer, without abundant fertilizers that derived from the availability of large-scale synthesis of ammonia. And you see the increase of the population. So the difference between these two is the effect of availability of fertilizers, which are induced from the availability of this synthesis method. So you see that, for example, the availability of food that we have today is largely depending on the chemistry. Of course, chemistry is very well integrating all catalysis and chemistry in all our life, from a refinery to chemical processing. Most of these processes, they are catalytic steps. And you have a very large impact because it's not only for this process, but for example, that one of the main applications that we have all handling is cleanup technology that we have on gas, on car, or many other systems. And the impact is very large because is inducing a large impact, which is about 1/3 of the overall GDP. This is another example, for example, taken from a company. This is Clariant, one of the main company, and this is the estimation of the contribution that they can have in improving the catalyst and improving the catalytic process that they have in terms of respect to business as usual. You see that they estimate that something like of the order of 13 exajoule can be saved by improving the actual existing catalytic process using, let me say, emerging catalytic technology. So, and of course, this saving corresponds to a large saving in terms of CO2 emission. And clearly, this required to have a better understanding, and you see on the bottom some element. For example, you need to understand what are the different elements in the catalyst. You need to understand the different processes which occur that we see again in these different scale, time scale, and length scale, the different kind of process that you need to control. And of course, going to this direction, you need to use as much as possible nanotechnology to design and to develop effective catalysts. Let me say that perhaps nanocatalysis is one of the first real example of industrial large-scale application of nanotechnology, which of course we have seen also before. You have many applications from energy to biorefinery, green process, environmental, food processing, or other like sensor. And what you see here is just one example that if you change the nano dimension and the different kind of phase which are exposed, even in a very simple reaction, which is oxidation of carbon monoxide, but which is an important reaction in terms of environmental application, what you have typically in the car, you have a very large dependence on the kind of shape of the nanoparticles. And going to a bit into long-term strategy, what we see is that this is a kind of estimation of what is the trends that we have up to now in different countries in terms of reduction of the greenhouse gas respect to the state which is today essentially. What you see is this black is the average of all, and this is the target that we have for 2050, which is net zero emission. You see that if you make an extrapolation of the current trends, you arrive to something like half of this. And you need to take account that it is more difficult, more going, you go to more deep decarbonization. So what is the message is that if you like to arrive to a net zero emission as agreed on political level, we need to accelerate the kind of technological development. And this is the reason why there is necessary to put a lot of attention on this aspect. And we see that, of course, cost is a very important part. What we see is that if we predict, for example, 2050, some of the cost for advancement for different kind of technology, we see that some are negative costs because they introduce in some way some alternative. For example, when you introduce electrical vehicle, you have a saving of energy, and for this reason, at the end, you have a saving of cost. There are some other in which, on the contrary, even in 2050, there are some higher costs. It is obvious that we have a lot of discussion also today on the use of electrical vehicle or hydrogen vehicle, which is very fine because they are an important part of the future. But what we need to dedicate attention is how we can really reduce the cost and so introduce better the technology for this other part, which is the part in which still we can predict that we will have higher costs. And this is important to go in this direction, which is the area which is called solar fuel. And we have different parts. We have some parts which are already available today, which are multi-steps, what we need. And we have seen also today that water electrolysis is one important component, but this will be not enough. If we like to address the challenges that we have for the future, we need to go to new generation of system that is called here full integrate or hybrid system, which are, for example, photoelectrocatalytic device, other system in which we reduce this and we improve the efficiency. And this was in some way introduced before. What we need is to combine all these elements to go from a linear model that we have today in which we extract a fossil fuel and we emit carbon dioxide to a model in which essentially we have a circular use of carbon through various technology, and here are just illustrated two electrocatalytic approaches and artificial leaves, but of course is much more complex the situation, but essentially in which we realize net zero emission because essentially we are circulating all the carbon that we are emitting. And this is long term, and one of the elements that also before was introduced that to reach this, we need to think in terms of globally, and we need to transport, we need not only to use hydrogen on produce it on local scale, but we need, for example, to transport, and to transport hydrogen itself is not easy, and we need to convert this to some hydrogen vector or other vector. Here you see some elements. So the picture that we have is more complex, and we need to see globally, and that we can produce globally energy, but we can transport renewable energy through suitable energy vector. And this is the reason why you can put all together, and you see that we have a very big challenges, but we need to dedicate time to try to develop some of the key technology that we need, not only for today, but especially for tomorrow. So, and finally, of course, one component of this is all the possibility to recycle carbon dioxide. Electrochemistry is one of the technology to go in this direction, not the only one, but is one of the key technology. And of course, in this way, we can just take carbon dioxide from emission and we can recirculate and so close the carbon cycle. And we have other elements like to have green ammonia production that we have seen also in this case. We need to develop a new technology and going in the direction in which we can have system like kind of artificial leaves, but in which respect to the natural leaf, we adapt the chemistry in order to make the fuel, in order to make ammonia, in order to make all the system that we need to transport. And in this way, for example, we have seen that this is meeting some two of the sustainable goal of United Nations, like clean energy and sustainable fertilizer. So this is the conclusion. We have an ongoing transition in energy and chemistry that will lead to a system change, and we need to understand, and we need to determining where are the technology, where are the critical elements to go in this direction. This is the limiting step that we have today. We need to invest, and we need to invest also in the future technology. Catalysis is one of these, but of course is one of the elements in a very complex picture, and we have today also some presentation of some of the other elements. But we need also to accelerate the progress. The kind of development that we have today is not enough to arrive to the target that we have. And for this reason, we need also to create some kind of community that work together in order to accelerate this process. Thank you.
Thank you. I'm really sorry with the last speaker for them being so late. So I invite Professor Pillar to give his speech. Thank you so much, and excuse me again.
Good evening to everyone, and good evening, Professor D'Assisti. Thank you very much for offering me this opportunity. And I am very happy to be with you and to share with you some ideas that have been developed according to my professional path. I just want to share a brief presentation of mine. That is this one. I hope you can see.
Okay, works.
Okay.
Just put it in presentation mode.
Yes, I try. Okay, I hope you can see now.
No.
Okay. Okay, so I am a computer scientist. I am.
No, we cannot see.
Giuseppe, we don't see the full screen.
We see the screen. You need
Yes.
to push on the. Giuseppe, Beppe,
Yeah.
guarda in basso, quella a destra. Sì, sulla riga, vicino al 70%.
Ma qui non c'è.
No, io credo che lui abbia già messo in modalità full screen, ma devi fare la condivisione dello schermo giusto. Quindi se vai in condivisione, seleziona l'immagine con lo schermo tutto aperto.
Ok, just 1 minute, proviamo. Allora, interrompi condivisione, adesso vado qui, presentazione di PowerPoint, ok, torniamo qui.
Dovrebbe essere un'immagine piena.
Sì, allora proviamo a partire con l'immagine piena. Adesso provo di nuovo a fare condivisione dello schermo e vediamo, niente da fare. No, ragazzi, non...
È buona così, vai.
È sufficiente?
Sì, dai.
Posso provare a ingrandirla in maniera tale che penso si possa vedere con chiarezza. Va bene. Allora, thank you very much to everyone for offering me the possibility to share some consideration with you. I will share with you some consideration more than some really scientific contribution. Because now I am involved much more in politics related to digital transition, and so we will share with you some consideration about how this digital transition can be used for sustainable development, and what are the relation between these two very relevant fields of interest. First of all, I want to start with some consideration related to the National Research Plan. I've been the coordinator on one table of the National Research Plan. It is a programmatory book, a report, then the Italian government uses to define the research activities of university and public entities. So it's very important. And now we have finished to develop the research plan for the period 2021-2027. So this plan will define the research of the entire country for 7 years. As you can see, the plan was divided into different pillars. The first of all concern e-health, then humanistic culture, creativity, social transformation, and so on, security, and then informatics, industry, and aerospace, climatic problem aspect, energy, and sustainable mobility. And the last pillar concerns sustainable technologies, agri-food, and so on. It's quite interesting that this definition gives us the opportunity to see some new concept, a new idea, and also the movement of some area of interest. For instance, for that concerning my themes of interest, it's quite interesting for me to observe that cybersecurity, that is generally considered as a topic of computer scientists, is now under the in the pillar of security for social systems. So cybersecurity is becoming a problem of the government, a problem of the nation, much more than a problem concerning computer scientists. These are very relevant movement in this map that give us a clear idea about some research topic and the different role that they assume in our country, in the society. So my field of interest concerned digital transition and industry 4.0, and therefore I worked on this topic. And also in the description that we have used, that we have arranged for the National Research Plan, we found some specific issues that are very strictly related to sustainable development. So it's quite interesting for me to use this time to share with you some concepts. First of all, concerning the problem of digital transition, I just want to stress that at the moment, Europe and Italy will have to face the double challenge of digital and green transformation. So we have a double objective that concern the digital transition, the digital transformation of the country, and also the green transition. These two different transitions should work together because, as we will show, they are very strictly related. And this is necessary in order to increase the modernity, efficiency, and competitiveness of the country. In this process, research on digital transition is a very relevant area of interest in order to allow the achievement of the SDGs of the 2030 agenda. In general, when we discuss about the digital transition, some very relevant point concerns, first of all, the integration that we will see every day in our daily life of different areas of research: computer science, electronics, and telecommunication. If we give a look to our smartphone, that is a device, an object that each one of us use, in this object we have an integration, a strict integration of computer science technology, electronics, and telecommunication. Smart device, intelligent devices are strongly characterized by this very strong interaction between these three different areas that in the past in scientific research were considered as a different domain of interest. Then we have strengthened the European research area, and we have to rationalize the landscape of available funding instruments. This is a very important step, because notwithstanding we are scientists and we are engineers and so on, we have to create a synergy between the funding rate, the funding opportunities, and the development of science, the development of technology, according also to new criteria for technology transfer. Then we have to relate the ICT area, that is the area in which I work, to all the areas of the National Research Plan. The ICT area is rightly considered now as a transversal area that is necessary to allow all the other areas to exist and to become more and more strong. For instance, without digital transition, we cannot really work on many areas of medicine, for instance, telemedicine, precision medicine, and so on, we cannot work on agri-food, we cannot work on future mobility and so on. Then we have to ensure the digital sovereignty of our country, because now the capability of the digital system is so big that if we lost the possibility to use them in a proper use for our country, this can reduce our digital sovereignty and the sovereignty of the institution on our nation. In our documents, we declined the digital transition into three main steps, into three main domains. Human-centered system, that are all the systems that are realized for the person, for the individuals. So all the technology that we can use in the next future for the single feature, the single person, and to enhance the quality of life of the single person, these are systems that will be developed under this area. Sustainable communities. Sustainable communities are the network of people that works in our city, that lives in our country, in our communities, in our territory. So we can ensure that these communities can use and must use the technology in order to be more and more resilient, more and more sustainable. Then we have another declination of digital transition that is directly devoted to the competitiveness of the country, of Italy. This is very important, and this, of course, involves all industry aspects. So we have these three areas in which digital transition can be declined to make it possible to achieve a value from the digital transition. Not only for fundamental research, but also to use digital transition to have some social, personal, and national impact. Of course, this is possible if we have a very strong technology asset, and this can be assured by heterogeneous device and system, so reinforcing research on heterogeneous device and system, and on networks of intelligent system. It is that are, of course, two fields much more related to specialists in computer science and engineering. Now, if we give a look in a more detailed form on a human-centered system, we can discover that many of these topics are strictly related to the SDGs. For instance, digital identities, social policies, welfare, public administration, justice, education, industrial processes. Just to give you a look, just to give you some examples of this area of interest. Then we have that educational technologies, the digital that is used to improve capability to perform very high education in a very fast way, in a very cheap way, and so to perform education in a way that is much more coherent with the need of our country, with the need of our industrial system. Then we have a technology to support the individual in the world of the work, and also for using cultural content and biomedical technologies. When we move from the personal sphere to the sustainable communities, for instance, we have the need to use the data for communities. And the problem of data is very relevant, as we will see in a few minutes. And so we have to use different data streams that in a community or in a smart city are produced by a very huge amount of different devices. And we have the necessity to integrate these different data to make them available to the community, especially in an open data format, and also to have the ability to use them in a proper way. Then we have, for this problem, we need new tools for using this data, to process this data. And in this sense, I want just to stress that the world of computer science is not perfectly ready in order to use this data. Every one of us knows terms like cloud computing and so on. They are really, they have been in a really way a very relevant revolution, no, in the computing world. But now this kind of approach shows some weaknesses because the amount of data becomes more and more bigger, and we are not sure that first we are able to use all this data, and second, it is necessary and useful to use all this data. Then we have the problem of course, administrative simplification and the necessity to define new working model that is directly connected to the SDGs needs. Then we have, of course, many other objectives, like, for instance, the sustainable management through digital transition of energy resources, because it's quite obvious that without a digital system and without digital technologies, we will not be able to move toward a sustainable development of our country. Then we have also the digital transition that has to work with the country for country competitiveness. So we have to support the paradigm of Industry 4.0. We have to define new model for cloud manufacturing. We have to define new workforce management system. We have to improve our data analytics system because we need now to work on a very huge amount of data, and in many cases the effectiveness of the results can be achieved only if we can use in a very real-time way. So we need a very strong computational power, and this also means a very strong energy that should be used for this kind of computation. Then we have, of course, also other action. I want just to focus one aspect that is very relevant, in my opinion, for this community, for this talk. The problem concerns the data. The data has been discovered as a very real value for our society. When I were young, computer scientists focused on program, on algorithm. No? We said that I have the algorithm, I have the program, and the value was concentrated on the idea of having a new algorithm, a new program. Now we know that the real value is conveyed by data, and therefore the data is assuming a very relevant value in all companies, in all institutions, and in the society. Among data, we need we want to focus the concept of open data, that are data that are open, that are freely accessible to everyone, without restriction of copyright, cost, and so on, and without any control that limits their reproduction, their use. Of course, open data imply transparencies, and is also they offer the possibility for everyone to use them, and then support the participation of also citizens to the public life, and this make institution much more stronger. So it's very important. They are used for public utility service, for companies, and of course for single individual. But if we were to develop a knowledge society, we need to face with the different relation. In this very famous picture, you can see different a cloud of different set of data and their relation. Each one of these relations should be strictly evaluated because there are some problems related to the order of the data. They're related to the access of the data, related to the amount of information that this data convey. And in order to face really with this in order to face really with this data, we have two aspects that are very relevant. The first aspect is related to the security. And in fact, we cannot imagine to develop a sustainable future if we do not are able to ensure that our data, that is our value, is secure. And so the field of cybersecurity has become more and more relevant, We cannot imagine how many attacks we have every day to our very relevant database, also at institutional level. You know, in Italy, there are more than 11,000 different locations in which public data are stored. Indeed, we are not able to assure security of 11,000 different locations in the country. So it's quite obvious that we need to reflect on this aspect and to define a new path that can put this data in a secure way. This slide is very interesting. In this plot, you can see the different types of critics events that can occur in the next future. And on the axis side, you can see the probability. So the event with the very high probability are of course in the right of your screen, and on the coordinate you can find impact. So the gravity of the problem that this event can occur. And of course, at the very critical part of the square, you can see the events that are related to the climate change. So you can see the failure of a climate action, weather extremely variable, loss of biodiversity, natural disaster. But in this position, you can see cyber attack. So cyber attack is becoming a terrifying event that is also that can occur with a very high probability. So it's quite obvious that we need to focus this aspect with a very, very high attention. And conversely to the common storytelling that says that don't know, Russian people make attacks and so on. In this map, you can say that the most attacked starts from USA and have as object something that is still in the USA. So USA is the most criminal state in terms of attacks that they produce, and also, of course, that they receive. You have to note that now is extremely easy to try to attack some website, some server, something like this. In the dark web, with less than $10, you can find a criminal as a service tool, and you can use this tool to attack something, some institution, some infrastructure, some ports, some hospitals, something like this. So this is a very important problem, and of course we need a very global strategy in order to face with this kind of worldwide problem. Unfortunately, it's not easy to move in this domain, because as you can see in this slide, if you in 1 minute of internet you move about 1 million terabytes, and in this 1 minute of internet, more than 4 billion users work on the net. And for instance, you can say that in only 1 minute you can have I don't know, more than 59 million messages sent by by WhatsApp. You can say that you have more than 190 million emails that have been sent. This is just in 1 minute. So the problem that we have is all these data are all necessary in order to design a better future. It's always necessary to have this amount of big data in order to extract knowledge and to use this knowledge for sustainability. Take care that we need a new trade-off between the amount of data that we store, and I want to stress that there is a cost in order to store each bit of our email, or each frame of a video, or each image of our camera. So we need the energy in order to store all this information. And the question is necessary to store all this material and so to waste the energy in order to design a sustainable future? So probably now we are moving toward a new world in which we can use technology, but in a much moderate way, because we need to define a nice trade-off between the technology that we need to use, and the sustainable world that we want to design. So this is our choice, and of course this decision must be taken at the country level, because it's quite obvious that there is a worldwide solution, but each country has its own degree of innovation, and we need to make some common decision in order to use technology and digital technology in particular in the right way. So this is what we want now on which we are working now, also at governative level. And in this frame, the role of human factor is very important, because we need that each person has to assume some individual behavior that must be aligned with a political and strategic framework of our country. On these themes, we are now working also with the national project and so on. I thank you very much for your attention, and if you have questions, I'm very happy to try to reply. Thank you.
Michele, you are mute. You need to unmute yourself, Michele.
Thank you so much, Professor Pirlo. And now we are a little bit late, but there are a lot of questions rising in the chat. So just Mario, suggest me how to manage. Can we take a little bit minute just to handle some of the most important, then let the single question to be solved with the speaker, or should we in any case go through all the questions?
Why don't we use just 5 minutes now to answer to some questions, and then given that the chat is recorded, I will send to you, Michele, and to Michelle, and you can try to identify who can answer to each of the questions in the chat.
Perfect, perfect. Okay, I think it's better. First of all, I just will stress to the speakers to upload their own presentation, because I guess there is someone is not already on the drive, so it's very important for you. So if I give in order, Professor Pirlo is here, so I know if you have to leave, you can just reply to the last 2 questions on the chat, so we can reverse the order if you want. There is some consideration they put.
May I try to reply?
Yes, yes. If you read it, it's okay.
Okay.
The chat. Barbara Frigione, right?
Barbara Frigione.
Is Barbara here?
Okay.
Yes.
Okay,
if
just
you
a
want to put
consideration.
directly the question, is okay.
Okay, thanks. Good afternoon, everybody, and thank you for this very informative presentation. So just a consideration, because during the last year, I worked a lot on the localization of Agenda 2030 indicators and looking for statistical data at province and urban level. I've noticed that one of the most important barriers is finding statistical data. Most of the time, they are just spread in many different official websites, but many times they are not open. And in my opinion, to define a strategy at local level, it is really important to have this data open. In fact, most of the time, also the municipality do not have this data for their territory, and they have to ask them to other agencies or other institutions. So I think that open data are really important, and most of all, maybe a unique platform in which we can all find this data. Thank you. This was just a consideration. I know that there is a problem of security. Also, the municipality of Brescia last year had problems with security. But is this possible? Is this it is possible to have a unique platform with so much data?
Thank you very much.
Thank you.
Thank you. Thank you very much for a very important question. Yes, of course, from a technical point of view, it's it's possible and quite simple to have a unique platform for instance, for all PR in order to store the open data and so on. The problem of data, in my opinion, is this. First of all, we have to understand that sustainability is not free. It has a cost, and also municipality and companies and so on should accept to pay a cost in order to work and move towards sustainability. Many times they don't want to do this. They don't want to pay any cost, and the cost means the person who have to work on the open data and so on. So this is a very big problem, and that is general, of course. And the second problem related to data is this: data, when data are available, they allow to make some decision that descend from the data. And many times it's much more easy to not have data, because so decision can be taken under different consideration. So I think that there are these 2 points for which we do not have a common tool, a common framework for open data in Italy. There is no very strict project on a platform of open data. First of all, there are no budget specifically devoted to this, with some rules that are strictly defines the way in which this data should be realized by each municipality and public entities. And it's not very useful to have this data. It's dangerous in many cases. They are considered not positive. And this is a cultural problem. And indeed, many universities are working on this. Many universities in all Italy are working on this, because I think that if we work on the cultural aspect, we will also able to change this idea and to move toward a more useful and more honest use of data.
Thank you so much.
No, yeah.
Okay, Thank you, Professor Pillo. So I think it's okay for your contribution.
Thank you very much.
Thank you so much again.
Bye.
And I tried to summarize a question. Maybe we can just, I saw that some speaker already reply in the chat. And but it seems the hottest topics is essentially the energy communities, the first group. And I saw some answer from Norma and from Marco. And another group is for Professor Quartarone concerning the LCA of electric car, which is still a very hot topic by now, so sustainability. Understanding if really electric cars are sustainable versus the standard combustion one. So I don't know if Eliana wants to add something on this, or if you got some references from LCA. Also, they put another question about sustainability of lithium extraction. And also they wish some topics or some suggestion for hydrogen technology from your side, of course. So if you wish to give some hints, I think we can summarize this way. Of course, if someone wants to intervene, it's okay to me.
Yes, life cycle assessment is very, very important and basic when you develop a new materials and design a new materials, because in your lab scale you can synthesize or produce the best materials ever. But if the sustainability in terms also of cost, economic viability is fundamental. So I don't know, I don't have any reference because it depends on the world of batteries and hydrogen is so large, so we probably I can find eventually and check, but it's so huge, so it's quite difficult to put some reference now. Regarding the, but in each project, for instance, funded by Horizon platform, LCA should be an important part of the project, of course, because you have to prove the sustainability and economic viability or the chemistry you are proposing. Regarding the lithium extraction, in terms of mining or in terms of batteries, because of course in terms of mining is another question.
No, it's not a question of mining, but you should consider for the LCA, of course.
Yes, of course, the recycling of batteries is a quite new topic. It's a very critical topic because up to now the batteries are recycled, but also only in order to recover cobalt, because it's the most valuable part now in the battery for ethical and also, of course, economic equation. Lithium is often sacrificed, but now take into account the reference of Battery Europe or other partnership in Battery Alliance, which are now defined, settled by the European Commission. Also, lithium is an important part to be, an important critical raw materials to be recovered. Thinking on the independency from the third country, as said before. Yes, there is some LCI study on it, not so rich of data at the moment. It's more complete for other metals, for instance, cobalt and nickel, not for lithium, because industry sector has not been interested until now in this kind of process.
If I can add something.
Sorry?
If I can add something on this.
Yes, of course.
First of all, I will suggest to students to refer much more than LCA on LCI, because means looking at the consumption of material and energy. So the inventory is much more sound than simply the impact assessment, because impact assessment goes through some things that are sometimes a little bit subjective, so they are not so strong from this point. To my point of view, it's much more better to refer to a physical balance. And so inventory, which is part of LCA, of course, is one of the important things. I studied the vanadium battery for a long time, and I know that this is very important. Eliana, of course, you will upload your presentation, which was really interesting. Really interesting. If you have some much more documents to give to the students,
Yes.
that will be really nice for us.
I can prepare a sort of list of reference that they can get. Okay.
Yeah.
Upload in the.
Okay, thank you so much. I tried to reply to the first question that was put by Saba El Shawa, that asked me how to assess the environmental impact.
Can I tell you that this morning the session was long and this afternoon is long as well. I think the students are quite tired after these 3 long seminars. So my suggestion would be to just answer by written the questions.
Okay.
So if we can collect them and we can you know, we can provide to them these answers later on. I really, they need also to take a learning test. I don't want they arrive at dinner time with this.
Okay, you have the feeling of the class, so it's okay.
Yeah, I think they are quite tired. It was very, very demanding.
Yeah, I saw. But anyway, I was going to close, so it's okay for me. So, okay, so thank you so much again. Thank you, Mario, for giving the room for sharing this session. And of course, I hope you all the best for your studies. And we are all available, of course, for all of you. Just write down a mail or however you wish to contact us, it will be fine for us. Okay, thank you so much and good day.
Thank you. See you then on next Tuesday 11. So you have a big weekend to rest, digest, and then on Tuesday you will be fresh again. Okay. Thank you, Michele. Thank you to all of the speakers. Bye.
Bye.
Thank you.
Thank you.
Bye.
Thank you. Goodbye.